Good morning, everybody, and welcome to part 1 of part 4. Although I verified my YouTube account today, so if this video goes over 15 minutes, we're going to give it a shot. I Googled it, and it says that's the secret. So let's do it. Okay, so yesterday we talked about writing maclaurin series. And hopefully you had a chance to look at some of those and writing some of those, writing the rule. And we actually came up with these two, with sine and cosine. And if you remember, we said that sine is all the odd orders, the powers of all the odd powers of x, the odd factorials, and oscillating signs. You will notice over here in the rule, because it's the odd powers, it's x to the 2n 1 over 2n plus 1 factorial. And then a negative 1 to the n is making the sign oscillate. Cosine, instead of being odds, is evens. So you generate evens with a 2n instead of a 2n plus 1. So notice its rule is to the 2n over 2n factorial. I would note here to be really careful. It seems silly, but you have to put the 2n in parentheses. Otherwise, you're only doing a factorial on the n. So you would be taking n factorial and multiplying by 2 versus only doing a factorial on the even numbers. So it's a tiny detail, but it does make a difference. What I want to show you in this video is how we can use these and one particular other one that if we have them memorized, we can really use them to shortcut and write some series that might otherwise take us a long time pretty quickly. So again, sine and cosine I would memorize. There's a lot. Your book has a list of a bunch you could memorize, but there's really 3 big ones: sine, cosine, and the last one is e to the x. So you can imagine e to the x is pretty straightforward considering that all of its derivatives are the same. And when you evaluate e to the x at 0, you get a 1. So all of the derivatives of e to the x are 1. So as a result, its series is the most straightforward series on earth. It's every single term, they are all positive, and all of the derivatives are 1s. So 1 plus x over 1 factorial, x squared over 2 factorial, x to the 3rd over 3 factorial, and so on and so on and so on. What you're seeing over here, these in r is equal to infinity, we're going to talk more about this in the later sections, but r is called the radius of convergence. It's basically handing you the interval of convergence. If r is infinity, then that means that the series is going to converge everywhere. So in other words, just like we saw with sine yesterday, the more terms you add, the better it will be, and the further out it will work from the center. So e to the x, sine x, and cosine x are all like that. Since they all have that same interval of convergence, we can make combinations of them, and we can write more complicated series. So let me show you what I mean. All right. This is the rule as it's written. It says on the intersection of their intervals of convergence, and sine, cosine, and e to the x are all infinity to negative infinity, so everywhere. We can take Taylor series and add them, subtract them, multiply them by constants, multiply them by powers, and adjust their arguments. For example, added, like I can take the series for sine x and the series for cosine x and add them together, and that gives me a series for the function sine x plus cosine x. You can subtract them. You can multiply them by constants. So in other words, if you want the series for 2 sine x, all you have to do is take the series for sine x and double all the terms. This one's pretty cool. Powers of x. So if you want the series for x cubed cosine, you can literally just take term by term all the terms of cosine and multiply them by x cubed. That is huge, because if you try to do that taking derivatives, this is a product. It blows up. Your first derivative is 2 products. Your second derivative is 4 products. Your third derivative is 8 products, and it is a disaster. So this is a great shortcut. AP knows it's a great shortcut, and we see it all the time. And this other one, arguments, can be adjusted. By that we mean like something like sine of 2x cubed, where this would require a chain rule. In your very first derivative, this would require a chain rule, and then after that, you'd be in this situation where you'd have a product every time. We can shortcut the series for that. So if you know the series for sine, I don't care what's in here. We can shortcut it. Now, it's worth noting this is only good for maclaurins. So if they ask you to write a series centered anywhere other than 0, you can't use these shortcuts. Sorry. Okay, so here's what I mean by adding them. It's kind of crazy. All right, so we know that the series of sine x is all the odds, right? So 1 minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7 over 7 factorial. And we know that cosine is the evens. So did I really do that? X. All right, so evens, 1, 1, minus, oh my goodness. Today, all right, 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so on. So what we mean by adding these together is to literally term by term do that. So I'm going to take, if I added these up, my first term is going to be 1. My second term is going to be x. My third term is going to be the x squared from up here. I'm just going to put them in order. My fourth term is going to be minus x cubed over 3 factorial. Your fourth term. So you just like go find the ones you need and rearrange them so that they're in order. Minus x to the 6th over 6 factorial, minus x to the 7 over 7 factorial, and so on. You're going to notice here, they're not going to ask you to write a rule for this because it would be really, really hard to write one rule that generates all these terms. Notice it goes plus, plus, minus, minus, plus, plus, minus, minus. Good luck generating that in sines. If they asked me to write a series for this, I would literally write the series for sine plus the series for cosine. You can, it's not that you can't then predict what the next terms are going to be. The next two terms would be, plus x to the 8th over 8 factorial and plus x to the 9 over 9 factorial, and then minus x to the 10 over 10 factorial, and so on and so on and so on. But you can really very quickly throw those two together, and it's allowed, which is kind of neat. Okay, so sine of x plus 1, like I always think this is a cute one. Again, so I have sine x, and sine x starts out with x, and then x cubed over 3 factorial, x to the 5th over 5 factorial, blah, 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 blah. And all I have to do is add 1. So normally I'd go plus 1 at the end, but this thing doesn't end. So I'm just going to go like this to put it at the beginning. Boop, done. Okay. Same thing with subtracted, right? But when we're doing subtraction, we have to be a little bit more careful. So again, I have my sine terms. And I have to subtract my cosine terms. So my cosine terms, you're going to notice all of theirs are going to change sign. To remember that that's a distribution. So again, I'm going to put them in order, but it's going to be -1 and then plus x, and then positive x squared over 2 factorial minus x cubed over 3 factorial minus x to the 4th over 4 factorial, and then plus x to the 5th over 5 factorial, and so on and so forth. Okay. But again, all you're really doing is putting the terms together in order. Okay, cosine x minus 1, this is kind of a cute one. Again, cosine x starts with the 1. I think I need to reevaluate what cute is. Okay, and it's -1, so literally I'm just going to come to the beginning of this series and be like, see you later, 1. You are no longer a part of this series. Now, if you take all the derivatives of these and use the Taylor formula that I showed you yesterday, you'll get the same thing, but please don't waste your time. If it's a maclaurin, you can use the shortcut. Okay. All right. These shortcuts where you can multiply by x's are probably the best ones. So by multiplying by a constant, it's literally like 5 times the series for sine. So if I wanted to write that as all it's doing for those of you who like to simplify, resist the urge in series, because like people might be tempted to rewrite this as 1 over 4 factorial. Don't, and here's why. What I want, if I want to write a rule, is to be able to see the pattern. And the pattern here is that you have a 5 in front of every term, and then you have the odd powers of x, and you have that same number factorial downstairs. All that is your cosine rule. I forgot my -1 to the n, being multiplied by 5. It's literally just the same series for cosine multiplied by 5. Okay. Where this shortcut rule becomes really, really, really handy, though, is when you can start putting the x squareds in. Again, like I said, if you tried to take repeated derivatives of this, you would go insane trying to do it. It would take you a very long time. Okay. We're not going to do that. We're literally just going to take x squared and multiply it by the series for cosine. So all of these powers are going up by 2. So my new series is going to be x squared minus x to the 4th over 2 factorial, x to the 6th over 4 factorial, x to the 8th over 6 factorial. So if I try to write a rule for that, I'm still going to have my -1 to the n. I still have my even powers in factorial. The only thing that's changed now is my x is no longer to the 2n. It's 2 more than that. It's now 2n plus 2. If you don't like that, you can write x to the 2n and write times x squared. That's also true. It's just that if you had x to the 2n times x squared, why not just rewrite it with one exponent? I'm just saying. Okay, so like, again, taking the derivatives of this would take a really long time. That is really, really quick. Okay. Here's another fun one that you can adjust the arguments of them. And here's what I mean by that. If you have the cosine, where's my mouse? I am a struggle bus today with my technology, and I apologize. Okay. If you have the cosine of x, we know the series, right? If it's the cosine of 4x, all we're going to do is go into that same series, right? And replace the x with a 4x. Okay. So this becomes 4x. Okay. In other words, my first term is still going to be a 1 because there was no x in it, right? And then it's going to be 4x squared over 2 factorial. 4x to the 4th over 4 factorial. 4x to the 6th over 6 factorial, and so on and so forth. That's it. It's that easy. Okay. So sine of x cubed. Whoa. Again, I'm just going to replace all the x's with x cubed. So my first term in sine would normally be x. Now it's x cubed. Okay. The second term would normally be x cubed over 3 factorial. It's now x cubed over 3 factorial. Okay. X cubed to the 5th over 5 factorial. X cubed to the 7th over 7 factorial. And again, resist the urge to simplify those. You can certainly write that as x to the 21, x to the 15th, x to the 9th. You don't need to, because when you know the rule for sine, so now when you go to write the rule for this, you still have, again, your 2n plus 1 factorial in your denominator. All you have to do is, instead of writing x to the 2n plus 1, just write x cubed to the 2n plus 1. Okay. Now, you could, since this is a power to a power, multiply those and rewrite this as 6n plus x to the 6n plus 3. Why? You know, there's no reason to. Just kind of keep it simple if you can. All right, so those are kind of the basic moves you can make. So what I wanted to show you is what happens. You can really write a fancy series. You may look at this and think, oh my gosh, I have to take a bunch of derivatives, but this is really just 3 adjustments all in one. So I kind of try to work, I guess, from the inside out is what I want to say. Like, first I'm going to write the series for cosine of 2x squared. Then I'm going to take that, multiply it by x, and then when I'm done, I'll take off the 1. Okay, so let's start with the series for cosine 2x squared. That's going to be my series for cosine with a 2x squared instead of an x. So my series for cosine, 1 minus all I'm doing is going to put a 2x squared in all these. 2x squared. Okay. To make that x times 2x squared, or x times cosine 2x squared, I'm just going to take all these individual terms, multiply them by x. So now it's 1 minus x 2x squared over 2 factorial plus x 2x squared to the 4th over 4 factorial minus x 2x squared to the 6th over 6 factorial. And then last but not least, I have that little adjustment that says minus 1. And so I'm going to fix it. I'm done. Here's my series. So instead of messing around with all those derivatives, in like a minute, I wrote a 6th order polynomial that mimics x cosine 2x squared minus 1. Pretty cool shortcut. All right. Okay. These are multiple choice, but I still thought that they were kind of worth checking out. This is the coefficient of x to the 6th in the series expansion about x for sine of x squared. Okay, so we know that in the x to the 6th term, oh wait, I just threw myself off. Never mind, I'm sorry. We know that sine is all the odd terms, right? So sine is x minus x cubed. If you don't know this one by now, I mean, seriously, I think I've written it 20 times in the last 5 minutes. Okay, sine of x squared would be all of these things squared, right? So the series for sine of x squared is going to be x squared minus x squared cubed. That's where your x to the 6th comes from, right? And then x squared to the 5th. That's your x to the 10th. So the coefficient for your x to the 6th term is negative 1 over 3 factorial, also known as negative 6. Okay. Now, in number 24, they're so kind as to give you the series for sine, and then they tell you that the derivative says if f is a function such that f prime is the sine of x squared, then the coefficient of the x to the 7th term. Okay, so f prime of x is the sine of x squared. So this is a series for sine x squared. They're saying this is the derivative. And then they want to know the coefficient of the x to the 7th term in f of x. You may be saying, well, there is no x to the 7th term there. Correct, they're not asking about that series. They're asking about f of x, which means they want the integral of that series. They took 2 tricks in one. Okay. So if I integrate this term, if I integrate negative 1 over 6 x to the 6th, I get x to the 7th over 7, so I get negative 1 over 42. Pretty tricky, huh? Now, again, you're not going to see multiple choice, but this could just as easily be like a part of a open-ended question. Man, I'm really on my game tonight. Okay, next video, we are going to talk about taking a Taylor series and centering it somewhere other than 0. Takes about 2 seconds. Wish me luck uploading a 20-minute video. See you later.